All right, today what we're going to look at is if we have a series and we look at the corresponding series where we take the absolute value of that series, meaning we take the absolute value of each individual term and add them up all the way through infinity, then that would be the absolute value of that original series. Our definition here says that a series A sub n is absolutely convergent if the series where we look at the absolute value of it is convergent. So kind of restating that, if a series A sub n is absolutely convergent, then it's known to be a convergent series. So we're going to look at some where we're going to use this absolute value method in order to say whether something is convergent or not. So let's take this series. We are going to try to determine if this series is convergent or divergent. So it's the series cosine of n over n squared from 1 to infinity. So like an example of a couple terms here, if you put in 1, it'd be cosine of 1 over 1 squared, then cosine of 2 over 2 squared, and so on. What we're going to do in order to do this one is we are going to look at the similar series here of the absolute value of cosine of n over n squared. And the reason we're going to look at that one is if we do that and we look at the absolute value of both the numerator and denominator here, we can say with certainty that if we take the absolute value of n squared, if we take any number and square it, it's still going to be n squared. It doesn't matter that we need that absolute value sign there because squaring something is still going to make it positive. What we can look at in the numerator, though, is if we take the absolute value of cosine n, we don't necessarily know what that will always equal, but we can kind of find a range of those values. If you think about the cosine graph, which looks like this, it starts at 0 here, and you've seen this wave graph before. Looks like this, and it just keeps repeating. If we look at what the maximum and minimum value of this can be, the maximum value is 1. The minimum value can be is -1. Well, if we take the absolute value of that, those values, absolute value of 1 would be 1. Absolute value of -1 would also be +1. So this series, at most, is going to be, or the numerator would be equal to 1. And so this series is always going to be less than or equal to a comparable series of 1 over n squared. Because the biggest that cosine, the largest value that this could equal with it being in the absolute value sign is +1, which we have here. Anything else, if we take any of these other values in between 1 and -1 and take the absolute value of it, it would give us a number that's less than 1, which would make this series value right here less than the 1 over here. Well, now we can say what we know about this, because this series right here is convergent by p series, because our p here of 2, our numerator, or our exponent of 2 here is greater than 1. So that one's convergent. So if we have a series over here then that's less than that, this one, or this series then we can say is convergent as well. And more than just convergent, we can say that it's absolutely convergent because the absolute value of that series is convergent. So this one's absolutely convergent by comparison. So what that tells us is that series is absolutely convergent, meaning that it also is just regularly convergent as well. So this one is a convergent series, and we can even go further by saying absolutely convergent. All right, let's have you pause the video and try one out, see if you think this one is convergent or not. All right, hopefully you had a chance to try that one out there. This one with that -1, let's take the absolute value of that, because we know that depending which number we put in here, this is either going to equal -1 or +1. The absolute value of both is 1. So we know if we take the absolute value here, that numerator is always going to be +1. The denominator will always be n squared, because absolute value of n squared is still n squared, which makes this one convergent then, or absolutely convergent by p series, because our p there, our exponent of our denominator is 2, which is greater than 1.